ventilation is the intentional introduction of outside air into a space. 1. Ventilation is mainly used to control indoor air quality by diluting and displacing indoor pollutants. It can also be used for purposes of thermal comfort or dehumidification when the introduction of outside air will help to achieve desired indoor psychrometric conditions. The intentional introduction of outside air can be categorized as either mechanical ventilation or natural ventilation. Mechanical ventilation uses fans to drive the flow of outside air into a building. This may be accomplished by pressurization, in the case of positively pressurized buildings, or by depressurization, in the case of exhaust ventilation systems. Many mechanically ventilated buildings use a combination of both, with the ventilation being integrated into the HVAC system. Natural ventilation is the intentional passive flow of outside air into a building through planned openings, such as louvers, doors, and windows. Natural ventilation does not require mechanical systems to move outside air, it relies entirely on passive physical phenomena, such as wind pressure, or the stack effect. Mixed-mode ventilation systems use both mechanical and natural processes. The mechanical and natural components may be used in conjunction with each other or separately at different times of day or season of the year. 3. Since the natural component can be affected by unpredictable environmental conditions, it may not always provide an appropriate amount of ventilation. In this case, mechanical systems may be used to supplement or to regulate the naturally driven flow. Outdoor air can also enter a building by infiltration, the uncontrolled flow of air from outdoors to indoors through leaks, unplanned openings, in a building envelope. In buildings that make no intentional design for mechanical or natural ventilation, circumstantial infiltration has been referred to as adventitious ventilation. In exhaust ventilated buildings, the intended flow of outside air may enter through planned inlets, but it will also enter through unplanned leaks in the building envelope. Generally, all outside air that crosses the building envelope through leaks is referred to as infiltration, whether it is driven by mechanical systems or natural mechanisms like wind. In many instances, ventilation for indoor air quality is simultaneously beneficial for the control of thermal comfort. At these times, it can be useful to increase the rate of ventilation beyond the minimum required for indoor air quality. 2 examples include airside economizer strategies and ventilation pre-cooling. In other instances, ventilation for indoor air quality contributes to the need for, and energy used by, mechanical heating and cooling equipment. In hot and humid climates, dehumidification of ventilation air can be a particularly energy-intensive process. In many scenarios, heat recovery ventilation can reduce energy use for heating and cooling by facilitating sensible heat exchange between exhaust air and incoming ventilation air. Energy recovery ventilation transfers moisture in addition to sensible heat. However, heat recovery can increase the fan power required for ventilation, and may increase energy use for heating and cooling for periods when ventilation would be beneficial for the control of indoor thermal comfort. The design of buildings that promote occupant health and well-being requires clear understanding of the ways that ventilation airflow interacts with, dilutes, displaces or introduces pollutants within the occupied space. Although ventilation is an integral component to maintaining good indoor air quality, it may not be satisfactory alone. 6. In scenarios where outdoor pollution would deteriorate indoor air quality, other treatment devices such as filtration may also be necessary. In kitchen ventilation systems, or for laboratory fume hoods, the design of effective effluent capture can be more important than the bulk amount of ventilation in a space. More generally, The way that an air distribution system causes ventilation to flow into and out of a space impacts the ability for a particular ventilation rate to remove internally generated pollutants. The ability for a system to remove pollution is described as its ventilation effectiveness. However, the overall impacts of ventilation on indoor air quality can depend on more complex factors such as the sources of pollution, and the ways that activities and airflow interact to affect occupant exposure. Ventilation should not be confused with air motion induced by ceiling fans or other devices. Air motion influences thermal comfort, it can decrease thermal stratification, and it may cause pollutant dilution by way of mixing, but it does not introduce outside air and therefore does not classify as ventilation. Ventilation should be considered for its relationship to venting for appliances and combustion equipment such as water heaters, furnaces, boilers, and wood stoves. Most importantly, the design of building ventilation must be careful to avoid the backdraft of combustion products from naturally vented appliances into the occupied space. This issue is of greater importance in new buildings with more airtight envelopes. To avoid the hazard, many modern combustion appliances utilize direct venting, which draws combustion air directly from outdoors, instead of from the indoor environment. Categories of ventilation. Mechanical ventilation refers to any system that uses mechanical means, such as a fan, to introduce outside air to a space. This includes positive pressure ventilation, exhaust ventilation, and balance systems that use both supply and exhaust ventilation. Natural ventilation refers to intentionally designed passive methods of introducing outside to a space without the use of mechanical systems. Mixed mode ventilation, or hybrid ventilation, systems use both natural and mechanical processes. Infiltration is the uncontrolled flow of air from outdoors to indoors through leaks, unplanned openings, in a building envelope. When a building design relies on environmentally driven circumstantial infiltration to maintain indoor air quality, this flow has been referred to as adventitious ventilation. Ventilation rate standards. The ventilation rate, for some buildings, is normally expressed by the volumetric flow rate of outside air being introduced to the building. The typical units used are cubic feet per minute, CFM, or liters per second, L/S. The ventilation rate can also be expressed on a per person or per unit floor area basis, such as CFM, P or CFM/FT squared, or as air changes per hour, ICH. Standards for residential buildings. For residential buildings, which mostly rely on infiltration for meeting their ventilation needs, a common ventilation rate measure is the air change rate, or air changes per hour, the hourly ventilation rate divided by the volume of the space, IRACH, units of 1/H. During the winter, ICH may range from 0.50 to 0.41 in a tightly insulated house to 1.11 to 1.47 in a loosely insulated house. ASHRAE now recommends ventilation rates dependent upon floor area, as a revision to the 62/2001 standard, in which the minimum ACH was 0.35, but no less than 15 CFM. Person, 7.1 liters/s/person. As of 2003, the standard has been changed to 3 CFM/100 square feet, 15 liters/s/100 square meters, plus 7.5 CFM, person, 3.5 liters/s/person. Standards for commercial buildings. Ventilation rate procedure. Ventilation rate procedure is rate based on standard and prescribes the rate at which ventilation air must be delivered to a space and various means to condition that air. 9. Air quality is assessed through CO2 measurement, and ventilation rates are mathematically derived using constants. Indoor air quality procedure uses one or more guidelines for the specification of acceptable concentrations of certain contaminants in indoor air but does not prescribe ventilation rates or air treatment methods. This addresses both quantitative and subjective evaluations, and is based on the ventilation rate procedure. It also accounts for potential contaminants that may have no measured limits, or for which no limits are not set, such as formaldehyde off-gassing from carpet and furniture. History and development of ventilation rate standards. In 1973, in response to the 1973 oil crisis and conservation concerns, ASHRAE standards 6273 and 6281, reduced required ventilation from 10 CFM, 4.76 liters/s, per person to 5 CFM, 2.37 liters/s, per person. This was found to be a primary cause of sick building syndrome. The 1989 ASHRAE standard, Standard 6289, states that appropriate ventilation guidelines are 20 CFM, 9.2 liters/s, per person in an office building, and 15 CFM, 7.1 liters/s, per person for schools, while the 2004 Standard 62.1/2004 has lower recommendations again. See tables below. In certain applications, such as submarines, pressurized aircraft, and spacecraft, ventilation air is also needed to provide oxygen, and to dilute carbon dioxide for survival. Batteries in submarines also discharge hydrogen gas, which must also be ventilated for health and safety. In any pressurized, regulated environment, ventilation is necessary to control any fires that may occur, as the flames may be deprived of oxygen. ANSI, ASHRAE, Standard 6289, speculated that comfort, odor, criteria are likely to be satisfied if the ventilation rate is set so that 1000 parts per million CO2 is not exceeded, while OSHA has set a limit of 5000 parts per million over 8 hours. Ventilation guidelines are based upon the minimum ventilation rate required to maintain acceptable levels of bioeffluents. Carbon dioxide is used as a reference point, as it is the gas of highest emission at a relatively constant value of 0.005 liters/s. The mass balance equation is, Q equals G/psi minus Ca, Q equals ventilation rate, L/Sg equals CO2 generation rate, psi equals acceptable indoor CO2 concentration, Ca equals ambient CO2 concentration. Ventilating a space with fresh air aims to avoid bad air. The study of what constitutes bad air dates back to the 1600s, when the scientist Maul studied asphyxia of animals in confined bottles. The poisonous component of air was later identified as carbon dioxide, CO2, by Lavoisier in the very late 1700s. Starting a debate as to the nature of bad air which humans perceive to be stuffy or unpleasant. Early hypotheses included excess concentrations of CO2 and oxygen depletion. However, by the late 1800s, scientists thought biological contamination, not oxygen or CO2, as the primary component of unacceptable indoor air. However, it was noted as early as 1872 that CO2 concentration closely correlates to perceived air quality. The first estimate of minimum ventilation rates was developed by Treadgold in 1836. This was followed by subsequent studies on the topic by Billings, 16, in 1886 and Flug in 1905. The recommendations of Billings and Flug were incorporated into numerous building codes from 1920s, and published as an industry standard by ASHRAE, the predecessor to ASHRAE, in 1914. Study continued into the varied effects of thermal comfort, oxygen, carbon dioxide, and biological contaminants. Research was conducted with human subjects control test chambers. 2 studies, published between 1909 and 1911, shows that carbon dioxide was not the offending component. Subjects remained satisfied in chambers with high levels of CO2, so long as the chamber remained cool. Subsequently, it has been determined that CO2 is, in fact, harmful at concentrations over 50,000 parts per million. ASHRAE began a robust research effort in 1919. By 1935, ASHRAE funded research conducted by Lemberg, Brandt, and Morse, again using human subjects in test chambers, suggested the primary component of bad air was odor, perceived by the human olfactory nerves. Human response to odor was found to be logarithmic to contaminant concentrations, and related to temperature. At lower, more comfortable temperatures, lower ventilation rates were satisfactory. A 1936 human test chamber study by Yaglaw, Riley, and Coggins culminated much of this effort, considering odor, room volume, occupant age, cooling equipment effects, and recirculated air implications, which provided guidance for ventilation rates. The Yaglaw research has been validated, and adopted into industry standards, beginning with the ASA code in 1946. From this research base, ASHRAE, having replaced ASHRAE, developed space-by-space recommendations, and published them as ASHRAE Standard 62-1975, Ventilation for Acceptable Indoor Air Quality. As more architecture incorporated mechanical ventilation, the cost of outdoor air ventilation came under some scrutiny. In cold, warm, humid, or dusty climates, it is preferable to minimize ventilation with outdoor air to conserve energy, cost, or filtration. This critique led ASHRAE to reduce outdoor ventilation rates in 1981, particularly in non-smoking areas. However, subsequent research by Fanger, W. Kane, and Jensen validated the Yaglaw model.